Megan, can you give next slide, please? Yes. So our work is mostly at the physical layer. So we're looking at millimeter wave architectures. And in the hardware, when there are fewer RF chains, one of the challenges we are trying to address is there is a reduction in dimensionality when you go from the antenna space to the baseband. So one of the main questions is how do you do this reduction in dimension without much compromise on the sensing ability? So we have some work going on what are called nested arrays. And then we complement these nested arrays with inference algorithms based on Bayesian techniques. So Rohan will have a poster discussing some of these ideas. So feel free to visit him. Another aspect we are looking at is a massive MIMO with 1 bit. This allows us to look at problems where there are nonlinearities in the hardware and deploy some machine learning techniques to try and deal with these nonlinearities. So machine learning, of course, we've been looking at machine learning for both receive and transmitter design, as well as for channel modeling. Okay. Can we go to the next slide? So here I have listed some publication in case you want to get some more details. Okay. The third publication by Govind Gopal, I want to highlight because he has a poster and he will be talking about distributed multi-antenna systems. Okay. So how to optimally place access points. The last two papers are really work we are doing on using machine learning for wireless communication. And the last paper was just recently accepted, so I'm happy to share some of the highlights. And Quan Lin has a poster and he can give you more details. Can you go to the next slide? Okay. So the topic is ResNEsts. This is residual nonlinear estimators. So our goal is to deploy, to understand these deep neural networks so that we can use them with confidence. And one of the things we want to do is be able to replace the building blocks in communication systems with some of these deep neural networks. Okay. And one of the common building blocks is linear estimation, and that's our first target. Can we go to the next slide? So let me provide some context so that when you go to Quan Lin's poster, you can get more details. Linear regression and linear estimation are common tools used in signal processing and communications. So for instance, if you are trying to estimate one random vector y given x, then the linear estimator that you have, y hat, is just an affine transformation on x. And you choose these matrices C and D to minimize the mean squared error. This is our linear minimum mean squared estimation. This is optimal when x and y are jointly Gaussian, but otherwise these are suboptimal. So if you want to go past linear estimation, then one way of doing nonlinear estimation is to create this random vector z from your measurement x. And phi1, phi2, phi-l are nonlinear transformations on x. So you basically create a new measurement vector z and then do linear estimation on using z. So you do nonlinear estimation, but it's embedded in a linear framework. The challenge with this, of course, is how do you generate phi-l, these nonlinear features, and often they're handcrafted. And with these deep neural networks, we have a chance to now really learn them from data. Next slide, please. Okay. So here I have shown you two deep neural networks. Okay. I know they are very hard to read, but the main point is just note that they have many layers. Okay. They contain many layers, and Yep. So as a result, these are very deep and very hard to learn and also hard to actually understand. Okay? And one of our goals is to try to provide some insight into these networks. Okay? The left network is a standard network, okay, where one layer feeds into the other layer. The second one is the more one that has recently gained more traction. This is called the residual networks. And the important part you can see is they have what are called skip connections. Okay, they have these connections that connect, that bypass layers. Okay, and these residual networks are this. I have the reference at the bottom. It was developed by this group in 2016 and are now widely deployed. Okay? The rightmost is basically showing you one building block that is concatenated to create the larger networks. Okay? So what we wanted to know is how do we provide guarantees for these residual networks? Okay? So that's really the main contribution of our work, is providing some insights on how to go about designing these networks so that you have some assurances they will meet a certain quality. Next slide, please. Okay, so I have basically redrawn the network, but have tried to hide unnecessary details. Okay, so believe me when I say this is the ResNet redrawn. Okay, there's one essential difference. In the last layer, we remove the nonlinearity and we just use a linear network. This is what we refer to as ResNest, is the residual nonlinear estimator. And explain a little more in detail. Okay. So when you look at this network, these W's are all simple linear transformations. Okay, so they are not nonlinear. The GIs are networks. They are usually shallow networks, so they are nonlinear, and so they operate on the input and provide nonlinear outputs. When you look at this network, the main thing we provide guidance on in this work is how to go about selecting different dimensions of this network. Okay? So one thing, let me provide some keywords here. One is an expansion factor. That means the W0, the first matrix. What it does, it takes the input and expands the dimension. And we provide guidance on how to do this and why it is important. The next thing are the VIs, V1, V2, VL that you see in the picture. Those are really nonlinear features. And we indicate that the dimension of these VIs must be smaller, so what are called bottleneck networks, so that we can make sure that the overall network can have some guarantees. The best way to visualize this network, by the way, is to look at V1. So V1 is a nonlinear feature. It appears directly at the output because of what are called the skip connections. It is transformed to W1, and then you have a path all the way to the output. So in a way, this network is generating nonlinear features V1, V2, VL, and then using some kind of linear transformation to actually get a final output Y hat. Okay. So even though the network looks very complicated, it's actually doing what was done previously, but except that the features are now being learned. Okay. There are few more things with this network that are problematic. One is that these W's that you use to predict the output also play a role in the feature generation, which is what we call the coupling problem. And so we suggest a network to try and avoid this coupling problem. Can we go to the next slide? So actually, when you start looking at it, you can actually write this as a linear estimator based on the nonlinear features that are generated in the residual network. Okay. So this equation 2 allows us to come up with some interesting guarantees. Can we go to the next slide? So here are some results. And one, so let me just highlight first two maybe, and you can go to Quan Lin's slide for the rest. One is we show that if you add more layers, if you do this properly, which is what we call the wide ResNest, which is the expansion factor and the bottleneck, you're always guaranteed to improve. The next one says that you can always do better than a linear predictor if you configure this network properly. This is very important because we use linear estimators all the time. So what we have been able to show is with the proper setting, you can replace all your linear estimators with nonlinear estimators, knowing that they'll always perform better. And the last item, we actually suggest a new network where things can be, more guarantees can be provided in terms of performance.